Hey everyone, so now we've seen a lot of techniques how to scatter in general and how to handle attributes when you scatter geometry, and also how to scatter into geometry via a volume. And I want to add to this a couple more things because it might be important in certain cases. And the first thing is when we use a scatter on a grid, then remember the first thing worth knowing is that when you increase the amount of points, the whole thing will get slower because the reason those points are distributed evenly is the relaxed iterations. And this is a process that takes calculation time. So if you don't need that because you want a huge amount of points, then turn this off. It will speed up the whole thing and you can scatter way more points. So this is something we already learned, but what's interesting now on top of this is if I wanted to copy geometry to this, let's say a sphere, and for this one I use a primitive sphere, and be careful to make this make sense, set the radius to exactly 1, because then it's basically, a unified sphere with exactly 1 meter radius, and then it will work the best, because what we want to look at now, currently the sphere will be too big when we scatter them, and we learned that we could just create our own Pscale here to solve this, for example with a vex code, and then we can set it ourselves. But there's actually already a built-in function in the scatter node under output attributes that you can activate called output radius attribute. And this will give you the correct Pscale dependent on your total point count, because it takes the whole area that it gets and divides it basically through the number of points. And here you can see when you change the point number, you will change the Pscale with it. Pretty handy. But what you notice is when you do not have the relaxed iterations on, that the spheres will not automatically calculate the right scale relative to the distance. Keep that in mind. Would be nice if it would do that, but it doesn't. It assumes that the relaxation is at a maximum. And here you can see now it makes sense. Only if the spheres are actually relaxed does this Pscale make sense. And again, if you now change the number, it will adjust the Pscale accordingly. Another thing we've already seen briefly is keep in mind that very often the absolute point number here is actually not that useful, because let's say we want a distribution something like this. Now if I take my grid and I would scale it up, you would see that the spheres go bigger, and because the distribution is basically changing when you think of it as how many points are in a certain area. And this is why very often it makes sense to not work with an absolute total count. And when I turn this off, you get a relative density scale. And I work with this quite a lot actually, because here now I can decide what the density should be. Let's say something like this. And when I change my input, this density will stay intact and the numbers will change accordingly. So very often that is more what you need in practical terms, because let's say you want to create a forest like we did in the beginning. If you want to make the forest bigger, of course, the distance between the trees should not change. And for this, the density scale is better. In this context, we've already seen also that you can paint the density attribute. So let's say we paint a mask here. And as I explained in the video, I would recommend changing the light settings to something less complex, because then you can paint quicker, because it will not try to calculate light on your painted mesh. So something like that. And then maybe we change the operation to smooth. Whoops, this one. And then we can soften this out a little bit. And when you take this attribute, which is mask, of course, as a density attribute, the cool thing now is you can see that the Pscale will actually adjust to it accordingly. So if I increase the density, let's say, and here you can see I didn't paint anything in the center. Let's actually make sure there's a little bit everywhere. So a very low density I'm painting here in the center, and then I smooth the whole thing. And then you can see that this density attribute will be represented in the scale, in the Pscale that comes out of your scatter node, which as you can see is pretty cool, because it allows you to do something that we will look at later on called circle packing. So you can make sure that when you use an attribute for scaling the spheres, that this attribute will also be represented in the Pscale if you use the output radius attribute here. And of course, painting attributes is not the only way of creating a pattern like this. We will see later on, you can also create the mask attribute that we used here with other nodes like noise or randomness or something like that. But this is for a later video. I just wanted to show you this so that you're aware that you can automatically calculate your Pscale. Now, a small addition to this, there's a new interesting tool in Houdini 20. The problem with this approach is that your attribute that you paint is always dependent on the resolution of your geometry. So what I mean by that is when you have a grid with no resolution whatsoever, an attribute paint will not work because we only have those 4 points that we can paint on. In certain cases, that's a problem. When you have complex geometry and so on, you don't always want to subdivide your geometry massively only so that you can paint an attribute. This is quite important for example, the fur or the feather system. And this is why Side Effects introduced a new system called texture mask paint. And the idea here is that this is not painting the attribute on the actual geometry, but into a virtual texture. The downside of this is that your geometry needs a UV space. So you need UVs on it. And we will talk about this later in another video. But for now, the quickest way of doing this is the node UV unwrap, which creates an automatic UV mapping on our grid, as you can see. And now the texture mask paint allows you to paint into this. And as you can see, independent of your geometry resolution, because it paints into this texture. And here is the resolution of this texture. Just imagine this as a texture in your RAM. And the texture is basically converted into a two-dimensional volume. Let's not go into this. And you cannot use this directly in the workflow that we've just seen. And because of that, Side Effects came up with a new node that can read this purely for scattering. And that is called scatter in texture mask. And you just have to connect those two outputs and inputs. You could use your own texture here, but if you wanted to use the texture from the texture mask paint, you just switch up here to texture primitive. And now you can see it uses this attribute that we were just painting for scattering. Again, the idea here is that you can do this independently of the resolution of your geometry. The grid here only has 4 points and 1 primitive, and yet we were able to create such a high detailed mask for our scattering. This is not something you don't have to use, but it's an interesting thing to know, and I didn't want to keep it from you. So this came in with Houdini 20. It might be an alternative for you. So play around with this. Maybe for a certain problem this can be helpful. But as you can see, it's a bit more complicated to understand. And then finally, what we've already seen as well is that you can, of course, scatter inside of an object. So let's say we take our box here and we can fill this with a volume, for example, with an ISO offset. That's one way of doing it. Or maybe a VDB from polygons. And we will talk about those nodes more later on. Keep in mind, with a VDB from polygons, you have to switch this to a FOC VDB. And either way, you now have a volume that you can scatter into. So something like this maybe. But the problem is that everything is evenly distributed here. So what if I wanted to have some, holes in here or something? I cannot use an attribute here because a volume doesn't have attributes. But what I can do, and this is more for you to know for later because we haven't talked about this yet in detail. When we know more about volumes, you will understand this better. I just wanted to let you know that you can actually, by changing this volume, also change where the points will be scattered. Because only if the volume has a value of higher than 0 will a point be scattered inside of the volume. And that means you could, for example, use nodes like the volume noise fog, which we will talk about in a later video, to create inside of your volume, which you have to name density for this to work. And then we don't add, but we set the density. And now what we can see, if we change the element size a little bit, you can see that our volume values are actually changing. And one way of changing the contrast is by remapping the values to something like this, for example. And again, I know this is a bit fast, but this is something we will look at later on and understand better. I just wanted to show you so that you just know this for now. When you scatter into a volume like this that has patches, then you will also get patchy points coming out of this. And this is a really helpful thing later on for all kinds of things. And I feel like when we talk about scattering points, I don't want to miss this important information. Again, the whole topic of volumes is something we will talk about in length in later videos. But for now, understand that if you scatter into a volume, the values of the volume itself will be taken into account when you scatter. And you can even use the technique that we learned before. You can now copy spheres on it and activate the radius attribute, which is of course the Pscale, and then you will actually see the distribution as long as your relaxed iterations are reasonably high. You can actually see this represented in the scale of the Pscale. You can see it's not perfect, so don't expect a perfect distribution here, but at least you can see it will be considered, so it will be part of the calculation. And this, as you can see, can be an interesting thing to create. So I hope this helped a little bit, understanding the scattering process even more. Play around with this to get a feel for it. And we will talk about volumes more in a later chapter. For now, I hope this is helpful. Thanks very much and see you later. Cheers.